be talking about a few things about data partitioning in distributed system. Here, basically, I'm going to talk about how do we partition the complete data in distributed system, and how in production the sorting will happen eventually. So mainly, I'm dividing the complete thing in three sections. The one the first section talks about how to decouple the keys itself, the keys and values that we are trying to store in database, in data store. And so here we will, in the first section, we'll talk about how to decouple the keys itself with the partition. And in the second section we'll talk about how to decouple the partition and the nodes. Okay, here the node means the actual physical machines, virtual machines, right? And in the third section we'll talk about the loose coupling of request and the responsible node. So basically here we'll talk about how the request is served from the backend to the client, right? As the data could be present on any node, so we'll see in that scenario how the data will be served from which node and how it is basically handled. So in the first, if we come to the first section, here basically partitioning will happen in the two way, right? The first approach is by dividing the complete data using the key ranges, right? And the another approach is by dividing the data based on the hash of the keys. Okay, so here let's take one example. We'll see over here. So let's suppose there are four partitions over here. So in the first section, as we saw, that data should be divided based on the range of the keys. So here let's suppose the partition 1 is responsible for taking all these keys who has lexicography starting A to C, right? From between A to C. And similarly partition 2 will handle between D to H. This is just an example. In production it could be different. So and P3 similarly I to T. And so we can see over here this gives an advantage, doing a range, sort of like a range query and range scan is much faster in this case, because we will be aware that on which partition the data needs to be queried is lying, right? So that will make it easier. But this partition division using the range of the keys. And the another approach is like we could do something like, we have, let's suppose, a key over here, and we apply a hash function, okay, over this key, and this will output an any let's say 32-bit number, right? 32-bit number. So we could in this case we could use any hashing mechanism, any simple mechanism also. Something like MD5 will also work. In the MongoDB itself uses MD5, and it uses this division where each of the partition will be responsible for some of the hash keys. So let's suppose P1 is responsible for all these hash keys which is between 0 to 8000, right? Similarly P2 is responsible for between 8000 to 16000, and so on. So this gives an advantage, like it sort of like it decouples the logic from the hash, the key itself, and the which partition it is going to lie. Because let's suppose here in the first scenario, this is the when we are storing based on the key ranges, right? So in this scenario, let's suppose any celebrity has any user ID. Let's suppose we are partitioning the data of any social media, right? And there is one celebrity whose user ID falls within I to T, right? Or maybe let's say A to C, which is a really small set of data, but we can see, right, if there are so many celebrities having between A to C, then this partition will have a lot of data, right? And the problem with this is, like, if we are taking the size of the partition has to be need to be considered in that case, that it must be higher, and it will cause a lot of problem during that scenario where any one of the partition can become a hotspot. So that is one issue with the key ranges if we are directly mapping the key with a partition. But if we are applying a hash function over a key and using that hash function's value to map to a partition, that will eventually distribute the data and distribute the load over all the partitions, and it will be a normal distribution. So yeah, so this was about the part loose decoupling the mapping of the keys to the partitions. Now let's talk about the second section, which is loose coupling between partition and nodes. So here are three approaches present. So let's suppose we had this very simple approach that comes to anyone's mind, that how are we going to map the partition to a particular node. Let's suppose I want to find, now we know that this particular key is lying on this particular partition, and now we need to find out where this partition is lying in a particular node, right? To find out that, one approach is like using a hash modulo n, where n is the number of nodes, and that will give you so in this case what's going to happen is, like, let's suppose there are four virtual machines, right? Four machines, and you have, like, let's suppose 12 partitions. Okay, so all these the hashing values of all the partition index will lie between 0 to 3, and what happens if we add more machines to our cluster? If we add more machines, then we have to rehash everything. We need to reshuffle all this data, because identifying the partition again would be a problem, right? Let's suppose if from four machines we remove one machine, or maybe one machine fails, then we are left with three machines, and in that case hash modulo will not work, because will be let's suppose if there will be some partition which is lying on the fourth machine, and we do modulo by 3, because now we will only be left with 3. So in that case we'll completely lose the data, lose the partitions which are available on the failed machine. So that is one problem with hash modulo n. So in this case it requires us to be have a fixed number of nodes and fixed number of partitions as well. We cannot reduce the number of partitions as well, so that is one problem. And in the fixed partitions, this is somewhat a bit better than the hash modulo n. Here in this scenario the partitions will be fixed, the number of partitions will be fixed, but the number of nodes can be rebalanced, right? So what I'm talking about over here, let's see with an example over here. So let's suppose initially we will have four machines, right? Four nodes. Each of the machines contain 5 partitions, so we have total 20 partitions, right? And what happens if we add one more node into the cluster, so that it can because we are experiencing the load spikes on our cluster, so we want to add more nodes into the cluster. So in that case, what will happen is the number of partitions will remain fixed, and let's suppose we are adding one more node over here, node 5. So in that case, what will happen is like it will steal one partition from each of the remaining 4 nodes. So it will have 4 nodes in total, and this partition which are marked with red, they will be part of this node 5. So this reallocation of partitions will happen when either a machine is added or removed from the cluster. So this is somehow decouples the logic of partition allocation between node and partitions, right? So here the number of nodes is free to change, right? But the number of partitions needs to be fixed. But this is also somewhat problematic in some scenarios where it might come a requirement that the number of partitions that we have is not sufficient to fulfill the incoming data. In that case, we need to increment we need to increase the partitions as well, right? Or maybe some partitions has unutilized some node has unutilized partitions, so in that case we need to decrease the number of partitions as well. So in that scenarios, what we need to use is the dynamic partitioning. So what dynamic partitioning does is it is sort of like a B tree data structure that we that is used in the databases, but you can it is just for the reference. It's not how exactly it works. So in dynamic partitioning, similar to like what it whenever the size of the node gets increased by some threshold, then it gets split into 2 nodes, and half of the node remain in half of the cells, half of the children remain in one node, and the half of the children goes to the another node, right? That's how it works in B tree. So that is a split mechanism. And if in the B tree itself, if you are removing the child, in that case it 2 nodes can be merged together as well, right? So similar to this happens in the partition allocation as well. So let's suppose in this dynamic partitioning, what happens is like initially any node will hold single partition, okay, which can be later increased as well. Okay, so let's suppose let me take one partition over here. Yeah, so initially if we start with it here, in this scenario both the number of partition and the number of nodes are free to change at any point in time. So let's suppose if this number of partitions is not sufficient to handle it, then we can split the data itself, right? So here it will create one more partition will be created, and half of the data will remain in this partition and half of the data will go into this partition, right? And and the nodes are also free to change as well. So if we let's suppose if we create one more node, we add one more node into the cluster, in that case as well, what's going to happen is like initially it will be it will have one empty partition, and let's suppose if you want to rebalance as well, so then in that case this partition will take some data from this one, some data from this one. So this rebalancing will happen internally. So that's what dynamic partitioning is. So both the nodes and the partition are free to scale at any point in time. And if let's suppose this one partition has really less data, and which can be accommodated within this partition, in that case a merge can also happen. So this partition will be merged to this one, and data transfer will happen uh, between these, right? So this is dynamic partitioning. So if we talk about the consistent hashing, consistent hashing is one form of a dynamic partitioning, you can say. Here, in that case, consistent hashing, number of nodes are also number of nodes can also change. Along with that, number of partitions also can change. Because we are if I would recommend, if you are not aware of consistent hashing mechanism, please check, refer some documents of consistent hashing. In that case, in consistent hashing, we see that whenever any node goes down, the number all these data which are part of the one partition, and that partition was part of the node which went down. In that case, a rebalance will happen, and whatever partition is next to whatever node is next into the clockwise in the hash ring, that will be accepting the node that will be accepting the data which were part of the failed node, right? Now let's talk about loose coupling the request and the responsible node. Okay, so there are three approaches we can see over here. One is client aware. So in this case, what is going to happen is, let's suppose we have all these nodes and partitions. Here one node is holding some data, this node is holding some data, and now client here wants to request some data which is either lying in let's suppose this partition, okay, or it could be somewhere else, right? So in that case, the client will be aware that this particular partition, because it is easy to find out this which partition does this key lies into, because we are using this hash function which will tell us that which partition is that data is present in. Now the problem is to find out which node that partition lies in, right? So in that case, in the client aware architecture, the client will be aware of the partition mapping to nodes. Here this we can take one example of, like, Slack uses this architecture, where each of the client has one particular shard assigned to it. So let's suppose there is one workspace in a company. So that particular workspace will be directly assigned to one-to-one map to a particular shard, and here client will be direct aware of that particular shard. So client can directly access to that particular shard, so it is very fast in that case. And yeah, it doesn't need request hopping in that case. So that's what client aware architecture helps in. And the another use case is another architecture is middle layer. We could introduce one middle layer, routing layer. So here, instead of this, we will have a routing layer. and the client will basically talk to routing layer. Okay, and the routing layer will have all this information within zookeeper. Okay, so routing layer will talk to zookeeper. Zookeeper will have all these configurations of all these details, like which partition is lying on which node. Okay, because zookeeper here will act as a coordination service, and it will have all this configuration of partition to node mapping, right? So all these details will be present in zookeeper. So this is middle layer architecture, where the client will directly talk to middle layer, and middle layer will give us the routing information, like which node that particular partition is present in, and then that particular then that request will be directly routed to the node which is responsible for that partition, and the request will be served from that node. And the third architecture is using server aware. So server aware architecture mitigates the use of this additional third party service, which is introducing routing layer and the zookeeper. So here in that case, let me remove this. In this case, client will directly talk to any one of the node. Okay, it's possible that the data that we are looking for is not present in this node. So in that case, what's going to happen is this particular node will route the request to the node which is responsible for the partition that we are looking for, the data that we are looking for, right? So here how this happens is by gossip protocol. So each of the node will be aware of all this configuration between other nodes, and each of the node will have all this list of mappings about all these partitions. So let's suppose over here node 1 will be responsible for, let's suppose, p1 to p5 partition, right? So in that case, each of the mapping node 1 to these 5 partition will be present in this node, this node 5 as well, and 3 and 4 as well. So that's how this gossip protocol works. Each of the nodes state, either it is alive or down or something like that, all these states will be present in each of the other nodes, so that even if the request comes to any one of the node, this request will be routed to the correct node which is responsible for the data, and the correct node will take that request, find the data, and hand it over back to the node that was requested from, and then this particular node will return the response to client. So that's how the server aware architecture works. So yeah, that was all about data partitioning.